So basically in this lecture we're going to start beginning to discuss quantum corrections to the classical theory. Okay, and so we've already discussed a lot of the properties that one would actually expect to see within the quantum corrections. And we discussed a lot about all the various divergence that could appear, what the physical meaning of these divergences are. So in this lecture, I'm going to give one explicit example. Okay, we're going to look through one particular classical theory and look at this quantum correction and see everything that I discussed in the last lecture, and we'll see it explicitly here. So this course is so this class is essentially the same class as last week, except in more details. Okay. So the Lagrangian we're going to look at is, of course, always the easiest if you want to understand various property of QFT, the scalar theory. And this is my Lagrangian. Okay. And we're going to look at the quantum corrections. The quantum corrections to what? To the scattering process. Okay, so we're going to have two particles coming in, two particles coming out. Okay, so this is going to be called as 1, 2, and this is 3, 4. So we know that there's a diagrammatic expansion in terms of the interacting vertex. So we have this vertex plus this diagram. And now you have two vertices here, and then we have more and more. Right? Now you would say that this is an expansion in terms of the coupling constant, lambda. Lambda squared, because this has two vertex and so on and so forth. Right? 所以这是一个你在做围绕，在对 lambda 做围绕，对不对？ But in the last lecture, we've noted this is more than just an expansion in lambda. And in fact, in a few minutes, we'll see that we're not actually considering expansion in lambda. We'll see that in a few minutes. But what is true is that this is really an expansion in terms of h bar. So this is 1 over h bar, because just to remind you, the propagator is proportional to h bar, and the vertex is proportional to 1 over h bar. And that's because your Lagrangian is sitting on top of h bar for 1 dx to the 4th l. Okay, so that means that the propagator, again, so this is, I'll just repeat myself again, because the propagator is the inverse of this quadratic operator, which carries a 1 over h bar, so therefore the inverse is proportional to h bar. Okay, and the vertex just carries directly this 1 over h bar here. Okay, 所以这永远都是这样子的，我们的 propagator。 因为你是从你的这个 quadratic 的 operator 的 inverse 去 define 的，所以你的 h bar 永远都是，你的 Lagrangian 有 1 over h bar 的话，你这 propagator 就会有个 h bar， 然后你的 vertex 的话，它的 h bar factor 完全就是从这个 1 over h bar 来的 ，OK， 所以这代表这个 vertex 有 1 over h bar， 这个有2个 propagator， 对不对？所以说它有2个 h bar 在这边，可同时又有2个 vertex。 所以有2个 h bar， 所以这是 h bar 的零次方。Okay, so there's 2 vertex here, so there's 2 factors of 1 over h bar, but then there's also 2 propagators, so there's 2 h bars. So this is h bar to the 0th power. So of course we're going to have h bar to the 1st power, and then so on and so forth. Okay, so I'm just, instead of writing dot dot dot, here I'm going to write an explicit, so that just means I'm evaluating things up to order h bar to the 1st power. Okay, anything beyond h bar to the 1st power I've dropped. So since h bar is 0 is the classical part, so that means that this is a classical interaction, and we're going to have the quantum interaction, which starts at h bar to the 0. So let's see what this interaction is. Okay, so today we're going to compute this quantum correction. Okay. Good. Now, if I just write down everything properly, then there's actually, because there's a, if we define this as m, so this is m, my my scattering matrix, then just to put all the right factors back in, because there's a minus here, so there's a minus and there's an I. So this is actually minus I. This minus is just because there's a minus here, and the I is just because you note that we have dx4, right? That means that usually we have a dx. One of them is time component, and we rotate to a Euclidean space, which is a factor of I. Did we discuss wake rotation last semester? 我们上学期有讲 wake rotation 吗？有吗？有没有人有印象？我是没讲啊，我不知道恒宇有没有讲。
好像没有。
没有是不是？这 OK，sorry。所以我需要稍微解释一下这 I， 其实这都只是一些 trivial factor， 这很容易就可以把它放进去。OK，basically 你问题是在哪？问题在于说我们习惯的是，我们真正积分是对 dx0、dx1、dx2、dx3、dx4， 对，但是我们不喜欢，那我们算了，太多。OK， 那我们知道 x0它的 signature 是负的嘛，对不对？它 x0上标跟下标，你的 metric 有个负号嘛，对不对？所以我们通常会喜欢做的事情是把它改成一个instead of Minkowski 的 signature， 我们会喜欢变成 Euclidean 的，然后叫做 dx0 prime、dx1、dx2、dx3， 那只是说我的 x0 prime 会给 I 再乘以 x0。所以这样子，我 x0 prime， 它用 x0的话，它的内积就是 r， 就可以用的是一般正常的那个嘛。那负的字一直 translate 到 x0的时候，会有个 extra i 的这个 factor， 所以这是个变数变换，所以你这个前面会有个，这时候你的积分就变成是一个Euclidean的积分，但是这前面会有个 i 的 factor 在这边。OK， 那这是为什么我们这边前面会有个 i 的 factor 会在前面呢？就是有个 vertex 会带一个 i， 但这 i 对我们来讲，在我们的这里面不会太重要。I'm just explaining that there's each vertex has a factor of minus I lambda. Lambda is just the coupling constant. The minus is because of here, and the I is just because to properly define this, we usually define this as a Euclidean integral, and then there's an h bar I sitting curve here, and that's where this I factor comes from. And of course, that also means that the propagator will have an I. So let me just put everything here. So this is really minus I lambda, and this will be a factor of I. Okay, good. All right, so let me just compute what this diagram is. So this diagram is minus I lambda squared. And now, so basically what we have, so here the vertex factor just gives you 2 minus I lambda to the square power. And the only thing relevant here is just 2 propagators. Right, so this diagram just contains 2 propagators. And so that means that we will have a propagator. So let me just call this momentum L coming in, and this momentum L minus P3 minus P4. Or let me just call this, okay, so let me just write this as L squared, and then L minus K squared, where K is just define K equals P plus P4. 我们就只有2个 propagator 嘛，这个 diagram 就只有2个 propagator 嘛，所以说我唯一需要写的是 factor 是这样子。那记得我们在写 Feynman diagram 的时候，里面每一条线我们都会去一定要满足这个 vertex 上面的 momentum conservation， 对不对？那所以如果说这边是 P1、P2 进来，就我这边这个叫 L 的话，我这个 propagator 的 momentum 只要是 L 减掉 P3 减到 P4 就会 satisfy momentum conservation， 因为这边会是 L 减掉 P3 减 P4 进来。再加上 P1 加 P2， P1 加 P2 会等于 P3 跟 P4， 这个 cancel 掉，所以这边就会回这两个出去。Okay, so this labeling of my momentum already solves the momentum delta function here. Okay, the momentum conserving delta function here. So this is what is important about loop, about quantum corrections that we discussed in our last lecture. When you start having quantum corrections, what happens, what is very special, is that now, because you have these internal loops, your momentum are no longer fixed. Right? This is what happens when you have loops, or when you have quantum corrections. The fact that your momentum is no longer fixed means that this L here, you need to sum over all possible L's. Okay, because essentially, if you want to understand why this is so, it's very simple, right? It's just because we need to sum over, you can think of it as you need to sum over all the states that are propagating. Now, since each momentum labels a state, you need to sum over all possible momentum. Okay, and since the momentum is continuous, that means you need to put an integral here. Okay, so we're doing this graph here. So this is minus I lambda squared, integrate dl. Now for reasons that you'll see soon, I'm gonna keep the dimension not fixed for now. Okay, so this is the answer to this problem. Okay, so this diagram means that this is a first quantum correction, and the answer is given by this integral. Okay, and we've seen from last time that if we're sitting in 4 dimension, because there's 4 L's here, and when L is large, there's also 4 L's here. So that means there's a divergence, right? There's a logarithmic divergence in this integral. So today, we're going to try to integrate this answer. Okay, I'm going to introduce a few techniques that you actually use for all the other integrals that you'll encounter in this class. Sorry, excuse me. Okay, so we're going to try to do this integral. So now comes the technical part. How do we actually do this integral? Okay, so first of all, I'm going to introduce so-called Feynman parameterization. So let me just give you the general identity, and we'll first prove the identity, and then we'll use it for this integral. So the general identity is, let's say you have a bunch of things in the denominator, a1, a2, all the way to an. Okay, that this thing is equal to gamma n integral the alpha 1 the alpha n, where the integration region is 0 to 1, and then delta 1 minus some I alpha I. Some, let me just write it down. Alpha 1 A1 plus alpha 2 A2 plus alpha n A. This is an identity. Whenever you have any products of objects in the denominator, you can always write it in this form and then combine all the products with this parameter here. Okay, and obviously you see what I'm going to try to do, right? Because there's a product of 2 propagators, and you see why this is useful, right? Because in general Feynman diagrams, you're going to have a bunch of propagators multiply with each other, right? So you want to combine them into a single denominator. And you'll see very shortly why this is a good thing to do. But I'm just going to introduce this as an identity first. Any questions about what I'm writing here? 所以我们现在要做这个积分，那事实上我们以后的积分都会是属于是这种形式，基本上就很简单，就是你基本上在积一个 rational function 嘛，你的下面会有一堆分母的东西，是因为你有一堆的 propagator 乘在一起嘛，跟某些分子的东西。那这个 identity 能够让我把所有的这个分母的这个部分，把它重新组成一个单纯的单一的分母。OK， 所以对这个 identity， 至少我现在会给它一个很快的证明，但是你们看这有没有问题？就是至少读它有没有什么问题？可以吗？好，没问题。OK， 我们来证为什么这个是 true。我们可以，这其实很简单，你可以先从2个开始嘛 ，e over a 再乘以 b。我 claim 说这个东西会等于1/0的积分 d alpha a 加1减 alpha b 的2次方，然后对，就这样子。OK， 你们可以试着去积看，这很简单嘛，对不对？这基本上你就只要我们可以积嘛，对不对？不用再做一次嘛。这你把它写成 alpha 的 a 减掉 b，再加 b 嘛的平 方嘛，那你把 A 减 B 把它做变数变换出来之后呢，就只单纯是 alpha 等于 G A 减 B 到sorry， 你把它做变数变换出来，对，从0到 A 减 B。那 alpha 带0到 A 减 B 的话，这个一个会是 A 分之一个会 B 分之一，然后最后你共同通分之后，积完之后你就得到 1/AB。我讲这很快，但是你们应该可以看出来，你可以自己试着做做看，这基本很简单嘛，就不错。所以我 claim 这个是 true。OK， 那如果这个是 true 的话，就代表说我这个积分可以把它改写成积分0到1，积分0到1比 alpha 比 beta， 然后 delta function 1减掉 alpha 减掉 beta 分之 alpha A 加 beta B。对不对？如果说这个东西是 true 的话，对不对？那这只是把这个边把它写成 beta 嘛，那 beta 的积分会因为这个 delta function localize 到 beta 等于1减 alpha， 对，所以这只是在改写，对不对？可是这个东西是不是就 precisely 就是这个形式？对不对？就是1减掉你把每一个 label 出来，然后把这个东西算在一起，这个 delta function 在这边。OK， 那所以你等于是证明了这个式子在 n等于2的 identity。那再你就可以用递回方式去证它。假设 n 成立 ，n 满足这个式子之后，那 n 加1的时候，你再乘上一个 extra factor 的时候，这边也再乘上一个 extra factor， 你是不是又可以套用这个在只有2个 factor 相乘的时候，我们就可以去证这个式子之后。Okay, so I'm just giving you a brief statement about how to prove this identity. Okay, you just start with 2, and this is just a very trivial identity that you can prove. So for 2, you can immediately prove this, and this, of course, already satisfies the general pattern for general n. So then you can just use a recursive proof. Assume that this identity holds for n elements. Just multiply an extra element an plus 1, and then you can recycle this computation again, and you get the answer. You get to show that this form actually holds for an plus 1. Okay. All right. So this is a very important identity that you will use very often. Okay. And the reason that you'll use it very often is precisely because all these quantum corrections take the form that has something with the denominator, and you want to put it in those single factor. OK， 好，所以我们如果有这个 identity 的话，我们现在就可以开始用它，用在这个身上，还是把它擦掉好。我用这个 identity， 就代表这个东西上是等于负 I lambda square，OK， 一样L的第4方2I。然后呢，这边就叫 alpha 1 L square 加，我把这个乘开来 alpha 2 L square 减掉2倍 alpha 2 L 大 K， 再加 alpha 2 K square 的平方。现在我要一个 integral 比 alpha 1比 alpha 2 delta 1减掉 alpha 1。Okay? Is this okay with everybody? Right, I'm just putting this into a common denominator. This factor is multiplied by alpha 1. This factor is multiplied by alpha 2. So I'm just expanding this factor out so you get these 2 pieces, these 3 pieces up. Everybody cool? Okay? Good. So once I do this, then of course, because alpha 1 plus alpha 2 is 1, right? So that means I can just erase this. This is just L squared times alpha 1 plus alpha 2. This is just L squared, right? So that means that this piece here, we have to use some color here. So that means that this piece here, I'm just going to rewrite this a bit. So this is just L squared. And moreover, this is L squared, so these two just becomes L squared minus 2L, L2, L dot K. So actually, I would prefer to write it as L minus alpha 2K squared. But of course, there's an extra k squared coming in here, so I need to subtract that out, L2 squared, k squared, plus L2 k squared. Okay, as you see, I've just made this a complete square here. Okay, everybody cool? All right, so here I can even do something a little bit more. So I'm going to rewrite this as L minus alpha 2 k squared. I'm going to pull this out. This is minus alpha 2, 1 minus alpha 2 k squared. The reason I'm pulling this out is because this alpha 2 here, this is just alpha 2 times alpha 1. Right? Because 1 minus alpha 2 is equal to alpha 1. So this is just alpha 1. Sorry.所以我现在可以把这个东西写成一个非常简单的形式，所以这边就可以写成负 I lambda square integrate dl square 2 pi 我叫它做 L prime 啊，等下你们就知道什么意思了嘛 d alpha 1 d alpha 2 delta 1减 alpha 1减 alpha 2 L prime 平方减掉 L1 L2变成很简单的积分了。首先，这 L prime 是什么意思 ？L prime 是代表我把这个东西叫做 L prime， 对不对？这已经是完全平方。那反正我在做这个积分，我可以把它，我要按针对谁积的，这只是 linear redefinition， 所以我就叫它叫 L prime。OK。所以基本上首先我要再说明一下，基本上我在这个里面所用到的所有的技巧，所有的 integral 的技巧，基本上就是你们在这堂常课里面会用到、反复用到的几个 identity。那只是说，在不同的 scenario 的时候，你们可能会用到的是稍微一些微小的变化，那基本上就是用这几个 identity。OK， 所以你们要熟悉，所以这只会是第一次演练，我们之后还会有持续几个不同的 process 我们都会用到。Okay, so we're at this level, so let me just rewrite the thing that we want to integrate again, because I'm now going to need some more identity. So yes, this is P4. So the thing now we want to integrate is square integrate the whole space of dl to the in d dimension 2 pi d L square minus alpha 1 alpha 2 k square. And then we have this d alpha 1 d alpha 2. Okay. Good. Now you see why this is a simple integral, because this is just L square, right? There's no there's no vector dependence on L. 这 L 基本上就是一个 L square 的这个 integral， 对不对？那通常这个 integral 我们会用另外的 identity。这种 spherical integral， 所以任何时候你有 integrate dl 的第一次方2 pi， 然后我今天讲的是 L square， 我们现在把它已经变成是 L square 加 delta。OK， 这边是 b 次方，这边是 a 次方。如果你是这样子的话，你得到结果上是4 pi，OK， b over 2。这我们上次有写过嘛？伽马 b 减 a 减 b over 2， 伽马 a 加 b over 2， 伽马 b 跟伽马 b over 2， 然后这边会是 delta 的 b 减 a 减 b over 2。Okay, so so we're going to use this into, of course, this is very simple. This is just L squared plus something. So this is the simpler version of this integral. But generally, you have this identity. This identity is very easy to prove. You can just do it yourself. I'm just going to sketch it for you. This is very easy. All you have to do is just rewrite this separate this into two pieces. One is the radial piece, and the other is the spherical coordinate, the angular piece, the d-dimensional angular piece. So that means you have 2b, you just write it as this, and then you have, of course, r d minus 1 dr. So now r goes from 0 to infinity, and here this is just a simple thing, or let me write it in a more suggestive form. This is just r squared a, and then r squared plus delta minus b. Okay, and then you need to multiply this by a separate factor, which is just d omega b. Okay, where this is just integrating over the spherical coordinates in d dimensions. Okay. 这个积分，我现在只要跟你讲说为什么这 identity 以后，我不要只是给你们写一个东西，然后你不知道为什么。所以这个 identity 基本上用到是 the fact， 你这个基本上只是你这 integrate over 一个 spherical sphere， 但是说这个 spherical sphere 你 integrate depend on distance 嘛，所以你可以把这个 omega 这个 angular coordinate 的部分 separate 开来，对不对？这样是让你们变成只是单纯一个 scalar integral， 把它简化成这样子。这我还可以再把它简化，这边会把它写成 2a 加 b 减 1。OK， 那再下来呢？再下来你可以做一个变数变换，你可以把这个东西把它做变数变换，把它变成一个积分从0到1 dx， 然后计算你的形式是1减掉 x 的，我还是把正负号把它弄反。哎，这是你的，我的东西在哪？你应该能够最后你要把它变成是 a 加 d over 2减 1， 然后 z 的1减 a 减 d over 2减1。你可以把这个积分，这个部分的积分，把它改写成这样的形式。OK， 基本上你可以想象嘛，第一个事情你先把这个东西去 redefine， 让这个变成 r， 这边是 r 减 delta， 这时候就有减1的部分出来，然后再来把 delta rescale away 就会有这个1的 factor。你就 rescale away 一个 delta， 你的 delta precisely 就会跑出来这个 overall 的这个 factor 在这边，然后你剩下是这个 integral， 那你会从原来是从，其实这个你一旦 shift 之后，这个会变成 delta 到无限大，那你 shift 完之后会变成1到无限大，所以你只要变成任何东西从1到无限大的话，你可以把它做个变数变换，变成从 dx 变成1 over dx。那 1 over dx 的话 ，x 就会等于是从0到1了。OK， 所以我就变这个积分的上下限。那你一旦得到这个积分的上下限，你得到，为什么下 x 以下 z？ 因为是 x。OK， 你一旦得到这个东西，是不是 precisely 就是 beta function， 就是 beta a 加 d 分之2跟 b 减 a 减 d 分之2。那 beta function 基本上就是这3个 gamma function 的相乘。OK， 那剩下的这个 piece 完全就是来自于这个 spherical sphere 的 integral。OK， 基本上如果你们到时候回去录影可以看到，反正就我刚刚讲的都已经录下来有证据嘛，就顺着我刚刚讲的那几个路去做。OK， 我这样就不用重复了。OK， 可是你们知道为什么我们刚刚要那样做？因为我们刚刚那样做的话，的确是可以把它变成一个 scalar integral， 这就不再 depend on L 的 direction， 这是 whole point 嘛，你希望 L 不要 depend on 任何的 direction， 这样你们就会比较好做。OK，good。所以如果我们利用这个 identity 的话， so if we're going to use this, so let's use this identity. Then this integral here now becomes I lambda squared. So essentially what we're doing is we're first integrating away L. Okay, so this is I lambda squared. Now if we're integrating L, we should just plug in this thing here. So 4 pi b over 2. So for here, for us, a is equal to 2. Sorry, b is equal to 2 and a is equal to 0, right? So since a equals to 0, so that means these two cancels out. So this means that we have gamma